Exercise 45. We are given an abelian group G here, and we have to prove that the set of all elements in G X that satisfy this equation, where E is the identity element in G and N is some fixed integer, is a subgroup of G. We have to first prove that thing, and then we have to give an example of a group in which the set of elements that satisfy this equation does not form a subgroup. So naturally the example must be of a non-abelian group, because in the abelian case the concerned subset always forms a subgroup. So let's first show that. Let A be the set of those elements X in G such that X to the power N is equal to E. Since E to the power N is always equal to E, no matter what N is, whether N is 0 or a positive integer or a negative integer, it does not matter. E to the power N is always equal to E. So we have E belonging to A. That's how we know that A is a non-empty subset of G. Now let X and Y be two elements in G. In A. We have to take elements in A because we want to show that A is a subgroup. Then X to the power N is E, and so is Y to the power N. Since G is abelian, we have X, Y whole to the power N equal to this, which is EE, that is equal to E, and X to the power instead of writing X to the power minus N, let's write this. By the rule of exponent, one of the rules of exponent, this is X to the power minus, or in fact we can straight away write this. So using this equation we get E again. Hence X, Y and X inverse both belong to A. This proves that A is a subgroup of G. Okay, now we come to the example where we have to show that this is not necessarily true if the group is not abelian. Consider the dihedral group D4. We know what its elements are. These rotations are 270 and these reflections. the set of all elements x in D4 such that x squared is equal to identity, which in this case of course is R0, R0 is this set. R0 of course will be there, R180 is also there because it's a rotation whose square, in fact it's a rotation with order 2, and then all the reflections are there, H, V, D and D prime. Okay, but this is not a subgroup of D4. Why? Because it's not closed under the operation in D4. This subset of D4 is not a subgroup of D4 because if we take the product of these two particular elements D and H of this subset, both D and H are in this subset, but this product turns out to be the rotation R270, which is not there in the subset. So that's why it's not a subgroup. And we already know that D4 is non-abelian, so we have our example. Then exercise 46. Suppose A belongs to a group A belongs to a group, that means A is an element of some group, and A has order 5. Prove that the centralizer of A is equal to the centralizer of A cube. Find an element A from some group such that the order of that element is this time 6, and this equation is not true for that element. Centralizer of A is not equal to the centralizer of A cube. Okay, so let's see the solution. since order of A is 5, so that means we are proving this first. We have A to the power 5 equal to the identity element in the group from where A is coming, and hence we are going to write an equation that comes from here, which in fact is this. We are going to use this equation in showing that these two centralizers are the same. Since centralizers after all are subsets of the group, so we have to prove that each is contained in the other as a subset. So let G belong to centralizer of A. Then G commutes with A, so automatically G will also commute with A cube. So GA cube can be written as GA square, which is AG A square. Then again this can be written as AGA A. AGA, and this becomes A square GA. We are freely using the fact that the operation in the group is associative. So that finally gives us A cube G, which implies that G is also commuting with A cube, and hence it belongs to the centralizer of A cube. So any element in CA is also in CA cube. Thus CA is a subset of CA cube. Conversely, let H belong to CA cube. Then H commutes with A cube, which implies we are now going to use this equation here. H A to the power minus 2 is equal to A to the power minus 2H. Thus, now what can we say about HA? HA can be written as H A cube times A to the power minus 2. So because of associativity, that product becomes equal to this. Now H commutes with A cube, so in place of this we can write A cube H. Again H commutes with A to the power minus 2, so this finally gives us AH. That means H also commutes with A. Thus H belongs to CA and we have CA cube also a subset of CA. Hence CA is equal to CA cube if the order of A is 5. Now we have to produce an example of an element from some group of order 6 for which this is not true, and that example again can be found in a dihedral group. Consider the element R60 okay, we can in fact consider two elements at once, R60 and F, in the dihedral group D6, where R60 is of course a rotation through an angle 60 degree and F is any one of the reflections. We have for these elements, we have order of R60 turns out to be equal to 6. You can verify this in fact. Also, R60 does not commute with F. So that F does not belong to the centralizer of R60, I mean CR60. However, moreover, this is true. This is equal to FR60 to the power minus 3. This is true. And because the order of R60 is 6, these two powers of R60 are in fact equal. So which implies F belongs to CR60 cube. Thus, CR60 is not equal to CR60 cube, where R60 is an element from D6 of order 6. So this completes the solution. 47. Let G be the set of all polynomials with coefficients from this set. We can make G a group under addition by adding the polynomials in the usual way. But there is a condition, except that we use modulo 4 to combine the coefficients. With this group operation, determine the orders of the elements of G. Okay, so that is one part of the exercise, and the other part is this. Determine a necessary and sufficient condition for an element of G to have order 2. Okay, so a general element of G is a polynomial where the coefficients are any one of these 4 numbers. So let fx equal to a0 plus a1x etc. plus anx to the power n be any element in G. That means these AIs are actually coming from this set. Note that four times fx, that is, if we add 4 copies of fx, then we get 4a0 plus 4a1x, because two polynomials, the way we have defined this addition by adding polynomials in the usual way. So this is done term wise. Terms of similar nature are added together. Two constant terms of the two polynomials will be added together, and two terms which have x in them, they will be, their coefficients will be added together. So like that we will add. Doing that, in this case we get this. And you can see that since this addition of the coefficients are addition modulo 4, so 4 times any element here is going to give us 0. Which is nothing but the 0 element of the group. So the order of fx is at most 4. For any element fx, the order is going to be at most 4. Now, order of fx is equal to, I think we can say something else also. You see, before going to the second part, we can say this. Note that we shall never have order of fx equal to 3. Okay, why, you may ask? Suppose fx belongs to G. Suppose there is such a polynomial whose order is 3. Then first of all, fx is not the 0 polynomial, because the 0 polynomial is the identity element in the group which has order 1. So then fx is not equal to 0, that is one thing. And also from this we see that 3fx is equal to 0. But at the same time 4fx is always 0 for any fx. Thus, 4fx is equal to 0. Thus, fx, which is nothing but 4fx minus 3fx, is equal to 0, which contradicts this directly. So because of this contradiction, our supposition is wrong. So no element in this group can have order 3. Okay, now what about elements of order 1? There is, of course, in any group there is exactly one element of order 1, that is the identity element. Now we have to finally conclude something, we have to find a necessary and sufficient condition for an element of G to have order 2. So now we go to the second part. Okay, note that for any fx belonging to G, we have order of fx equal to 2 if and only if okay, if and only if, what can we say? If we use this same expression for fx, then fx first of all is not equal to the identity element, the zero polynomial, and 2fx is equal to 0. That means 2a0 plus 2a1x etc. plus 2an x to the power n must be equal to 0, and this is equivalent to if and only if. Okay, now if we are, since we are choosing the AIs from this set, what are the possibilities for each AI, so that 2 AI is equal to 0 modulo 4? The possibilities are 0 and 2. 2 times 1 is 2, which is not 2 modulo 4 is not 0. 2 times 3 is 6. 6 modulo 4 is 2, which is again not 0. So only 0 modulo 4 is 0, which is 2 times 0, and 2 times 2 is 4. 4 modulo 4 is 0. So that's why we can write the necessary and sufficient condition like this. It's because we want an equivalent condition or a necessary and sufficient condition that we are going on writing if and only if. It means implies and is implied by, or logically equivalent. If and only if AI is equal to 0 or AI is equal to 2 for each I lying between, where did we start, 0. So this is a necessary and sufficient condition for an element of G to have order 2. Okay. Then exercise 48. In each case, find elements A and B. Please excuse the background noises. Okay, there something is going on outside which is not in my control. A and B from a group such that A and B have order 2, and there are 3 parts. AB has order 3, then B, AB has order 4, and C, AB has order 5. We Indians like to create extreme noise. Okay, so let's see the solution. The examples for part A and part C involve symmetric groups of the symmetric group of degree n, which we have not actually come across in this book. In chapter 5 only we will come across it, but I could not think of any dihedral group example working in this working for these situations. If you think for some time, you may come up with some dihedral example that works in this situation. The middle one, there of course I have the group D4 where we can produce two elements for which these things happen. But for the first and third one, I am going to use symmetric group. So I am going to I will explain what I am going to write, but it may not be exactly something you already know. So in part A, we consider these two elements. Let A comma B be the functions. Because we don't yet know what these things are, I am going to write the things I am going to write the things elaborately. Given by A of 1, so this is the definition of the functions. A of 1 is defined to be equal to 2, A of 2 is defined to be equal to 1, and A of 3 is defined to be equal to 3. Like that, B of 1 is defined to be equal to, so this one is 2, 3, okay, 1. So B does not change 1. B of 2 is defined to be equal to 3, and B of 3 is defined to be equal to 2. Okay, so let us now see what this is all about. It is a fact that if one considers the set of all functions from this set into itself, all of which are bijective, that means all of which are one-to-one and onto, then this set of bijections from this set to itself forms a group under composition of mappings, and that group is denoted by the symbol S3, and it's called the symmetric group of degree 3. Just like that, in place of 3 you can have any positive integer. So our first example is actually the symmetric group of degree 3, S3. There we have considered these two particular functions. Now the first thing we have to see is that you can in fact see that both the functions are bijective. Okay, each one of them is one-to-one and onto, so that means they are in S3. And now we have to see that with respect to composition of functions, they both have order 2, and moreover their product is going to be a function that is of order 3. So let us first see that they have order 2. To see that quickly, I am just simply going to mention the fact here, because when we get to symmetric groups in chapter 5, that these things will become obvious. So we will quickly see the thing here using this arrow diagram. Okay, now A takes 1 to 2 and it takes 2 to 1. It does not change 3. you consider A once more, you have this. So that means if you calculate A square, that just simply means applying A to each element 2 times, okay, one after another. So A square of 1 is what? First A of 1 is 2, and then A of that 2 is again 1. So this is equal to 1. A square of 2, just like that, A of 2 is 1, and then again A of 1 is 2, and A square of 3 of course is 3 because A itself does not change 3. So we see that A square is actually the identity mapping of the set onto itself, and that identity mapping turns out to be the identity element of the group S3 that we are talking about. So that tells us that order of A is 2. In fact, that actually tells us that A square is that identity mapping. But since A itself is not the identity mapping, because it does change something, right? It changes 1 to 2 and it changes 2 to 1. The identity mapping does not change any element. It keeps everything fixed. It maps 1 onto 1, 2 onto 2 and 3 onto 3. So that combined with this tells me that the order of A is 2. Similarly, you can verify that the order of B is also equal to 2. Let me wrap this part off. Now that we have understood why the order is 2, note that order of A equal to order of B is equal to 2. Now the function AB, which again is going to be a function from this set to this set, is given by, we can directly calculate the values. B of 1 is what? B of 1 is 1, and on that one, if when we apply A, we get 2. Okay, so this is equal to 2. In fact, let me just show it for once. A of B of 1, that's what AB of 1 means. So this is A of 1, since B of 1 is 1, and this is equal to 2. Like that, AB of 2, so B of 2 is 3. On that 3, if we apply A, then we get 3. Okay, and finally AB of 3, B of 3 is 2 and A of 2 is 1. Okay, and just like we verified that A and B have order 2 each, I urge you to verify that AB in fact has order 3. One can verify that order of AB is 3. Oh, we have not written anything about where the functions are coming from. No? Consider the functions. Let me write it here in S3. For this notation, you see chapter 5. I hope I am referring it correctly. In chapter 5, we have the symmetric group of degree n, Sn. Okay, so this is our first example. In the second one, we have our familiar dihedral group, and the example is this. For the reflections H and D in D4, we have definitely, because H and D are both reflections, they are of order 2, and order of HD, which turns out to be the rotation R90, has order 4. So we have got that example, and finally again we are going to use the symmetric group example for this. A and B are of order 2 and AB has order 5. Again, I repeat, you can in fact find dihedral group examples so that things look much more familiar to us. C. Let A comma B be the functions, let's write somewhat more briefly, from 1 to 3 to itself, oh sorry, it's not 1 to 3 anymore, 1 2 3 4 5 to itself given by A of, and this time we have to write a little more because there are 5 points in the domain. So A of 1 is 2, A of 2 is 1, A of 3 is 4, A of 4 is 3, and A of 5 is 5. Okay, like that. B of 1, okay, so this is 1 3 2 5. B of 1 is 3, B of 2 is 5, B of 3 is 1, B of 4 is 4, and B of 5 is 2. In the symmetric group of degree 5, one can verify that these elements also have order 2 in this group. The function AB, I need more ink, the function AB is given by a B of 1. B of 1 is 3, A of 3 is 4. Okay, AB of 2, B of 2 is 5, A of 5 is 5. AB of 3, B of 3 is 1, A of 1 is 2. Then AB of 4, B4 is 4, A4 is 3. And finally AB of 5 is going to be 1 because we haven't had 1 here. B of 5 is 2, A of 2 is 1, yes. One can means you should, okay, one can verify that in the group S5 the order of AB is 5. Okay, next exercise 49. Suppose a group contains elements A and B such that order of A is 4, order of B is 2, and there is an equation satisfied by A and B. A cube B is equal to BA. Find the order of B. Okay, using this information we have to find the order of B, and we are going to proceed like this. Note that A cube B, or first we in fact have to make use of these things. Note that A to the power 4 is equal to E and B square is equal to E. That these are coming from here. Also A cube B equal to BA implies if we pre-multiply both sides by A, we are going to have A cube B is equal to ABA, which implies A to the power 4B is equal to ABA. Since A to the power 4 is identity, so on the left side we have B and on the right side we have ABA. Okay, now post multiply both sides by B. That gives us, or do we have to, okay, I took down the wrong question. We have to find the order of AB. Okay, that's why we are proceeding like this. Let me just see whether I made any other mistake. A cube B is equal to BA. No, everything else is fine. So here we have B square equal to ABAB, which is nothing but AB whole square, and this implies E equal to AB whole square. Okay, so we have got an equation where there is a power of AB, a positive integral power, that becomes equal to the identity. So this equation tells us that the order of AB is either 1 or 2. It is 1 if AB itself equals the identity, otherwise it's going to be 2. So now we are going to argue that it cannot be equal to the identity. Suppose AB is equal to the identity, then B is equal to A inverse, and we know that an element in a group and its inverse have the same order, and so order of B, which is equal to 2, we can write like this: 2 equal to order of B will be equal to order of A inverse, which must be equal to the order of A, because an element and its order have the same, what the hell am I saying? An element and its inverse have the same order. So this is equal to 4, a contradiction. Hence, we must have AB not equal to identity. Thus, order of AB must be equal to 2. Okay, it has to be exactly equal to 2. Then 50. Suppose A and B are group elements such that order of A is 2, B is not equal to the identity element, and ABA is equal to B square. Determine, in this case we have to find order of B. Okay, so like that one, we are going to start with what is given to us. Note that A square is equal to the identity. Also, where is the equation? ABA is equal to B square. B square implies B is equal to A inverse B square A inverse. But since A square is equal to the identity, so A inverse is actually equal to A. So we can write, in fact, in place of this A inverse, A B square A inverse, which implies, now I could have written just simple implication sign itself. Now what we are going to do, you see, we have got an expression for B here in terms of A and B again. That expression we can use here. not on that side but this side. So on the left side we have b, on the right side a. In place of b we are again going to use this expression a b square a inverse square a inverse. So this implies b is equal to, now if we calculate this, what do we get? ab square a inverse, again ab square a inverse a inverse, and this is equal to, this is a square. You see, a inverse and a will become identity and will vanish in the middle, leaving us with b square, that is b to the power 4, and here we have a to the power minus 2. Now in this product a square as well as a to the power minus 2 are both equal to identity, so this is equal to b to the power 4. That means b is equal to b to the power 4, and that implies, since we are in a group, b cube equal to identity. Okay, now if b square is also equal to identity, then b equal to b cube times b to the power minus 2 equal to identity. A contradiction to what? A contradiction to this part of the hypothesis. So we cannot have b square equal to identity. So you see that neither is the first power of b equal to the identity, nor is the second power of b equal to the identity. Only the third power is equal to the identity. That means 3 is the smallest positive integer such that the corresponding power is equal to the identity. Hence, order of b is equal to 3. It must be exactly equal to 3. Okay. Now an exercise of a somewhat general nature. Like these exercises, these 1 or 2 exercises we have come across just now, but of a general nature. Let A be a group element of order n. Where n of course is some positive integer, and suppose that D is a positive divisor of n. Prove that the order of this power a to the power d is equal to n divided by d. First of all, we observe this thing. Using the rules of exponent, this is equal to a to the power n, which is equal to identity. One more thing you note is that since n is a positive integer, and because it's an order, it is by definition a positive integer and d is a positive divisor of n. So n by d itself is a positive integer such that this power is equal to the identity. Our aim is to show that n by d is the smallest positive integer for which this equation is true. That means there can be no positive integer smaller than n by d such that a to the power d to the power that positive integer also becomes e. We have to prove that that cannot happen. Suppose, to the contrary, suppose there exists a positive integer, say m, strictly less than n by d, such that this power is also equal to e. Then from this inequality we have or in fact we can write like this, then md is a positive integer such that it is strictly less than n and a to the power md, dm, md same thing, is equal to e. So we have found a positive integer such that this corresponding power is equal to e, but this contradicts this statement that n is the order of a and hence by definition is the smallest positive integer for which a to the power n is equal to e. So that thing is contradicted. But this contradicts the hypothesis that the order of a is n. So n by d is the smallest positive integer for which this is happening, and without writing anything much more, we can now directly conclude this. So you can see that if you take powers of a given element, then the order, the higher the exponent is, the smaller the order is. Okay, so next 52, we now come to matrix groups. Consider the elements this time are matrices, 2 by 2 matrices, 0, minus 1, 1, 0, and b equal to 0, 1, minus 1, minus 1. Okay, in or from SL2, R. That means the special linear group of 2 by 2 matrices where the entries are coming from the field of from the system of real numbers. Special linear because these are matrices all of whose determinants are equal to 1. Okay, so now find the order of A, the order of B, and the order of AB. And there is a question also. Does your answer surprise you? This part is not mathematical because it may or may not surprise you, say. So to calculate the orders, we just have to calculate the powers. We have A itself is not equal to the identity matrix. So that means order of A is greater than 1. So we have to look at higher powers. Oh, it would have been better if I was able to write it in one line. Unless I write the matrices side by side, it is somewhat difficult for me to calculate. Because based on this linear arrangement of writing, I have got a muscle memory of doing the calculations mechanically. So 0 times 0, 0, 0, minus 1. So this is minus 1. 0 plus 0, 0. 0 plus 0, 0. Minus 1 plus 0, minus 1. So that means A square is also not equal to the identity. What about A cube? A cube is A square times A. Zero plus 0, 0. 1 plus 0, 1. 0 minus 1, minus 1. 0 plus 0, 0. This is also not equal to the identity matrix, but we will find that A to the power 4 will become the identity matrix. So this is A cube times A. Zero plus 1, 1. 0 plus 0, 0. 0 plus 0, 0. 1 plus 0, 1. Yes. So order of A is equal to 4. Next, we calculate B square. So B is this. Zero minus 1, minus 1. 0 minus 1, minus 1. 0 plus 1, 1. Minus 1 plus 1, 0. Okay, what about B cube? Oh, so B square also is not equal to the identity. Now B cube is B square times B. 0 plus 1, 1, minus 1 plus 1, 0, 0 plus 0, 0, 1 plus 0, 1. So here BQ becomes the identity matrix. So order of B is 3. Next, what about AB? 0 minus 1, 1, 0, 0, 1, minus 1, minus 1. So AB becomes 0 plus 1, 1, 0 plus 1, 1, 0 plus 0, 0, 1 plus 0, 1. Observe that, okay, let's write the calculations in the middle. One plus 0, 1, 1 plus 1, 2, 0 plus 0, 0, 0 plus 1, 1. 1, 2, 0, 1, 1, 1, 0, 1. This one will make you realize that we are never in fact going to get the identity matrix. 1 plus 0, 1, 1 plus 2, 3. This element, the first row second column element, keeps increasing, keeps getting larger and larger. 0 plus 0, 0, 0 plus 1, 1. In fact, one can prove by induction, which is quite straightforward, that this is equal to 1n 0 1 for all positive integers n. So AB is of infinite order. So although A and B are elements of finite order, but their product gives us an element that is of infinite order. That is the element of surprise in this exercise. Then (53). Consider the element A equal to that element, that matrix AB from here in this special linear group. What is the order of A? We have already seen that this matrix has infinite order. If we view that same matrix in the special linear group of again 2 by 2 matrices, but this time the entries are coming from the finite system ZP of integers modulo P, where P is a prime. What is the order of it? In the second case, in the second group, the order is going to be finite. So the solution is like this. We have already seen in the solution to the previous exercise that as an element of SL2, R, A is of infinite order. And as an element of this group, however, again from this equation you can see that the order of A is going to be P. One can verify that the order of A as an element of SL2 ZP is P. One can means you should verify and make it a part of the solution. In fact, in this form the solution is incomplete. We are just simply mentioning that the order is going to be P without actually verifying it, but you supply the missing steps. Then exercise 54. Okay, this one is about rotation in 2 dimensions. For any positive integer n and any angle theta show that in the group SL2, R, again that special linear group, we have this equation, this matrix equation, matrix identity, minus sine theta cos theta to the power n equal to cos n theta minus sine n theta. The second row is sine n theta cos n theta. Okay, use this formula to find the orders of this particular matrices. Cos 60 degree minus sin 60 degree, sin 60 degree, cos 60 degree, and cos root 2 degree minus sin root 2 degree, sin root 2 degree, cos root 2 degree. Geometrically, this matrix represents a rotation of the plane by theta degrees. The first part of this exercise, of course, it has to be proved using induction on n. We first prove the given identity. This is looking awful. I should have ideally written n theta within brackets, but you can understand what we are trying to say here. Okay, the claim is trivially true for n equal to 1. You have 1 here, you have 1 here in place of n. They are actually equal to the same matrix, which is equal to this matrix itself on the right hand side also. Assume that the claim is true for some positive integer n, then So in this step we are going to use the induction hypothesis, namely that the claim is true for n theta minus sin n theta cos n theta sin theta cos theta. Now we perform the multiplication. So okay, it's going to take a lot of space. Cos n theta cos theta minus sin n theta sin theta. Then we have to write another entry here, minus cos n theta sin n theta, or sin theta, minus sin n theta cos theta. Sin n theta cos theta plus cos n theta sin theta, and then minus sin n theta. Okay, we can write it like this also, cos n theta cos theta minus sin n theta running out of space sin theta. Okay, now we use standard trigonometric identities. Cos n theta cos theta minus sin n theta sin theta is cos n theta plus theta, or in other words cos n plus 1 times theta. Okay, sin n theta cos theta plus cos n theta sin theta is sin n plus 1 times theta, but we have a minus sign, so minus sin n plus 1 theta. Here we have plus sin n plus 1 theta, and again cos n plus 1 theta. So you can see that this has the same required form. So this completes the induction. Now with the help of this formula we have to find the order of such a matrix where in place of theta we have 60 degrees. Note that cos 60 degree is cos 60 is 1/2 cos 2 times 60 degrees is what? Cos 120 degrees. So this is cos A cos B minus sin A sin B, or we can use that thing also. This step is not needed. Cos 2 theta is cos square theta minus sin square theta. Minus sin square theta. Sin 60 is square root of 3 divided by 2. That means, okay, am I getting it correctly? cos 2 theta is cos square theta minus sin square theta, fine. So cos 60 is 1 over 2, sin 60 is root 3 over 2. The point here is that we are not getting 1. Okay, in these cosine values we are not getting 1. That's the point. The actual value does not matter. Yeah, it is going to be positive because the angle is in the second quadrant. So the point here is this: these are not equal to 1. But we see that this is also not going to be 1, no? Because it's 180 degrees. This is equal to minus 1. But (240 degrees), and that will be equal to, I have forgotten all the trigonometric tricks that allows one to do these calculations quickly. This is frustrating anyway. So this is cos 2 times 60 degree. So that means, I need this value. 1 over 4 minus 3 over 4, that gives me minus 2 over 4, so minus 1 over 2. And that is also not equal to 1. This I think is going to be 1, but to make sure that I have that, I have to actually find the value. So that means we could have used this formula also, 2 cos square theta minus 1. Now this is also not giving me 1. So is it, have I made a mistake? I mean, there is of course no mistake in the exercise itself, but I am finding it difficult to go through the calculation, and I am finding it difficult to guess the order actually. Okay, let me just think geometrically. Cosine becomes 1 when? Cosine becomes 1 when the rotation is, it takes us back to where we started, I mean in the initial position. Cos 0 is 1, cos 2 pi is 1, cos 4 pi is 1. Okay, like that. Cos minus 2 pi is also okay. So instead of okay, fine. Instead of going through these awful calculations, we can argue like this. Cos n times 60 degrees equal to 1. if and only if, since n is for us a positive integer, n times 60 degree is 2m pi for some positive integer m. Oh, I cannot write pi here because we are using degree measure on this side. So that means m times 180 degree. M. So the smallest value of the smallest positive value of n is going to be what? So this is going to give me 3. Since m itself is positive, so n is equal to 3. N is equal to 3. That's why, okay, n is equal to 6. Note that sine 6 times 60 degrees is also equal to 0. Hence, this is equal to 1 0 0 1 and no smaller positive integral power gives us the by 2 identity matrix. Thus, the order of this is 6. And using this technique, I want you to show that the order of the other matrix where we have root 2 degree is actually infinite. There we are never going to get the identity matrix for any positive integer n. That part I leave to you. You may be wondering why I am rushing through all of this towards the end. It's because a very big noise disturbance is about to start outside. That's why. Okay, so I end the video here and we will continue with the other exercises in the next video. Until then, it's me, Lucifer, from a mathematical room. Have a nice day.